Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The early decades of the 20th century witnessed a profound transformation in the landscape of mathematics, a period of intense exploration, and the shattering of long-held assumptions. Within this era of intellectual ferment, a singular voice emerged, a mathematician whose contributions, though initially overlooked, would eventually reshape our understanding of geometry and its intricate relationship with algebra. That voice belonged to Ruth Moufang, a name now synonymous with groundbreaking advancements in the field. Moufang's journey commenced within a mathematical world grappling with fundamental questions about the nature of space and the foundations of geometry. Euclid's postulates, for centuries considered the bedrock of geometric truth, were under scrutiny. Mathematicians were beginning to question the universality of these axioms, exploring the possibility of geometries that diverged from the familiar Euclidean model. This burgeoning field, projective geometry, offered a fertile ground for such investigations, promising to unlock deeper insights into the structure of space. At the heart of this endeavor lay a critical tension: the desire to create more general geometric frameworks while preserving the elegance and coherence of mathematical systems. Traditional approaches, rooted in the established edifice of Euclidean geometry, presented limitations. These models, though powerful, struggled to encompass the full spectrum of geometric possibilities. The prevailing challenge was to develop new geometric models that could accommodate the complexities of non-Euclidean spaces. The early 20th century saw a surge of interest in projective planes, geometric structures that extend the familiar Euclidean plane by adding points at infinity. These planes, defined by axioms governing points and lines, offered a means of exploring geometric properties in a more abstract and generalized setting. However, a significant obstacle arose: the existence of projective planes that defy the well-established theorems of Euclidean geometry, such as Desargues' theorem. Desargues' theorem, the cornerstone of projective geometry, states a specific relationship between triangles in perspective. The discovery of planes that failed to satisfy this theorem presented mathematicians with a significant challenge. These non-Desarguesian planes revealed a surprising level of complexity and a need for new mathematical tools to understand them. The exploration of these non-Desarguesian planes became a central focus of Moufang's research. She recognized that the key to understanding these complex geometric structures lay in their algebraic underpinnings. Geometry and algebra, though seemingly distinct, are intimately connected. The coordinates of points in a geometric space can be represented using algebraic structures such as fields or division rings. Moufang understood that the properties of the underlying algebraic structure directly influenced the nature of the corresponding geometric space. If Euclidean geometry could be represented by fields, then what algebraic structures corresponded to non-Desarguesian planes? Moufang's work addressed this fundamental question. She pioneered a new approach to classifying projective planes, moving beyond the limitations of existing models. Her innovative strategy utilized the algebraic structures associated with these planes. She recognized the need to move beyond the familiar properties of fields, which are commutative division rings, and explore more general algebraic structures. This was a significant departure from the conventional methods of the time. Rather than attempting to force non-Desarguesian planes into existing frameworks, she sought to create new algebraic tools tailored to their unique characteristics. Her approach involved a deep dive into the properties of these algebraic structures, particularly those related to division rings. Division rings, also known as skew fields, are algebraic structures that share many properties with fields, but the multiplication operation is not necessarily commutative. Moufang's systematic investigation of these structures laid the groundwork for a new understanding of the relationship between algebra and geometry. The impact of Moufang's work extended far beyond the immediate realm of projective geometry. Her contributions laid the groundwork for a deeper understanding of more complex geometric structures. Her work provided a new framework for classifying and analyzing projective planes, inspiring further investigations into the relationship between geometry and algebra. Moufang's work, though initially met with limited recognition, has profoundly influenced the development of modern mathematics. Her insights into the connection between geometry and algebra continue to resonate today. Her pioneering work on alternative division rings and her groundbreaking contributions to the classification of projective planes demonstrated the power of abstract algebraic methods in solving geometric problems. Her legacy is one of profound intellectual innovation, a testament to her ability to perceive the hidden connections between seemingly disparate branches of mathematics and to construct the tools necessary to unlock their secrets. Following her initial breakthroughs in projective geometry, Ruth Moufang turned her attention to the abstract algebraic structures that underpin these geometric frameworks. This shift represented a significant move a transition from the concrete visualizations of geometric figures to the exploration of the fundamental algebraic properties that govern them. The mathematical landscape of the time presented a series of challenges, particularly in the realm of generalizing the well-established properties of fields, which are commutative division rings, to more expansive algebraic structures. Mathematicians sought to loosen the constraints of commutativity and associativity, characteristics fundamental to the arithmetic of real and complex numbers, and to explore the consequences of these relaxations. The prevailing mathematical understanding of the early 20th century was heavily rooted in the properties of fields. These structures, characterized by commutative multiplication and the associative property, served as the foundation for much of algebra and analysis. The desire, however, to model more complex geometric structures, those that defy the limitations imposed by Euclidean geometry and its algebraic counterparts, spurred the investigation of more general algebraic systems. The challenge was to determine which properties of fields could be retained and which could be modified, while still maintaining a coherent and useful algebraic structure. The goal was to build a bridge between abstract algebra and the intricacies of non-Euclidean geometries. Moufang's approach was systematic and innovative. She delved into the study of alternative division rings, algebraic structures that relax the associative property of multiplication. In these rings, the associative law, which states that the order of operations in a multiplication chain does affect the result, was replaced by a weaker condition, the alternative property. This property stipulated that any two elements, along with the product of one with itself, must associate in any order of multiplication. This seemingly subtle change opened up a vast new area of exploration, allowing for the construction of algebraic systems that could model geometries beyond the familiar Euclidean framework. A central element of Moufang's work was the identification of the Moufang identities. These are specific algebraic identities that hold true in alternative division rings. They provided a set of rules that governed the behavior of multiplication within these structures. The Moufang identities, a series of equations, revealed fundamental relationships between elements of the ring, allowing for a deeper understanding of their internal structure. These identities, a set of constraints, provided the tools to analyze and classify alternative division rings. They served as a compass, guiding mathematicians through the complex terrain of non-associative algebra. The significance of the Moufang identities extended far beyond mere algebraic curiosity. They provided a means of constructing and analyzing alternative division rings in a systematic manner. By exploiting these identities, Moufang was able to demonstrate the existence of new and interesting algebraic structures. She uncovered connections between different types of alternative division rings, revealing a rich tapestry of algebraic relationships. This systematic approach, focused on identifying and exploiting fundamental algebraic properties, distinguished her work. Moufang's innovative methodology lay in her ability to connect abstract algebraic concepts with concrete geometric problems. She recognized that the properties of alternative division rings could be used to model and understand non-Desarguesian projective planes, geometric structures that violated the principles of Euclidean geometry. This connection, a bridge between algebra and geometry, was a groundbreaking insight, offering a new perspective on the relationship between these two branches of mathematics. Her work demonstrated that algebraic structures could serve as a powerful tool for exploring and classifying geometric objects. The impact of Moufang's work on the development of abstract algebra has been profound. Her systematic investigation of alternative division rings laid the groundwork for the subsequent development of algebraic structure theory. Her work served as a catalyst for further research, inspiring mathematicians to explore other non-associative algebraic structures, such as Jordan algebras and Lie algebras. Her insights into the Moufang identities and their significance continue to inform modern research in algebra. The modern relevance of Moufang's work extends to various areas of mathematics and computer science. While her specific results on alternative division rings may not be directly applied in the same way today, her contributions have significantly influenced the development of abstract algebra, which is a fundamental tool in many fields. The principles she established for constructing and analyzing algebraic structures are relevant to modern mathematicians working in areas like coding theory and cryptography. These fields employ algebraic structures to design error-correcting codes and secure cryptographic systems. The understanding of algebraic structures, directly traceable to Moufang's work, is thus essential. Furthermore, Moufang's approach or focus on identifying and exploiting fundamental algebraic properties continues to resonate with contemporary mathematicians. Her work serves as an example of how abstract algebraic methods can be used to solve problems in other areas of mathematics and science. Her legacy is one of profound intellectual innovation, a testament to her ability to perceive the hidden connections between seemingly disparate branches of mathematics and to construct the tools necessary to unlock their secrets. Her work continues to inspire mathematicians to explore the frontiers of algebraic structure theory. The intellectual landscape of geometry during Moufang's era was undergoing a period of profound transformation. The classical edifice, largely built upon Euclidean principles, faced challenges from emerging non-Euclidean geometries. These new geometric systems, which challenged the fundamental assumptions of Euclid, stimulated a search for more general frameworks. Within this context, projective geometry offered a powerful methodology for unifying and extending geometric concepts. Projective geometry, with its focus on the properties preserved under projection, provided a flexible and encompassing structure for investigating geometric relationships. However, even within this framework, limitations remained. A central problem was the status of Desargues' theorem. This theorem, a cornerstone of projective geometry, states that if two triangles are in perspective from a point, then they are in perspective from a line. While true in many projective planes, it did not hold universally. The existence of projective planes not satisfying Desargues' theorem, known as non-Desarguesian planes, presented a significant challenge to the understanding of projective geometry. These planes, while geometrically valid, introduced complexities. They demanded new methods for their description and classification. The challenge was to understand the algebraic structures underlying these non-Desarguesian planes and to relate them to their geometric properties. Moufang's groundbreaking contribution lay in her ability to connect these geometric structures to algebraic concepts. She recognized that the algebraic properties of the coordinate system used to define a projective plane directly influences geometric properties. Her work focused on the construction and characterization of a specific class of non-Desarguesian planes, now known as Moufang planes. These planes, unlike the more familiar Desarguesian planes, presented a more complex and fascinating landscape. Her approach was deeply innovative. It involved linking the geometric properties of the plane to the algebraic properties of the underlying coordinate system. She demonstrated that the coordinate systems of Moufang planes could be described using a specific type of algebraic structure, an alternative division ring. An alternative division ring is a structure that satisfies all the axioms of a division ring, with the exception of the associative law for multiplication. This seemingly small deviation from the standard algebraic rules resulted in dramatically different geometric consequences. Moufang's construction of the Moufang plane involved a meticulous interplay between algebra and geometry. She carefully defined the algebraic properties of the alternative division ring and then demonstrated how these properties translated into geometric relationships within the projective plane. This approach allowed her to build a concrete model of a non-Desarguesian plane and to analyze its properties in detail. This was a significant achievement as it provided a tangible example of a projective plane that violated Desargues' theorem, thus illustrating the broader possibilities within projective geometry. The impact of her work extended beyond the specific example of the Moufang plane. Her approach established a powerful methodology for bridging the gap between algebra and geometry. It demonstrated that geometric properties could be understood and classified by studying the algebraic structure of their coordinate systems. This insight opened up a new avenue for research, allowing mathematicians to explore the connections between different branches of mathematics. The innovative aspect of Moufang's work lay in her ability to see the deep connections between seemingly disparate areas of mathematics. She recognized that the geometric properties of a projective plane were intrinsically linked to the algebraic properties of its coordinate system. This allowed her to use algebraic tools to analyze and classify geometric objects, and vice versa. She was not simply applying known algebraic methods to geometry. Instead, she was creating a new, integrated approach that transformed both fields. The Moufang plane, as a specific example, serves as a powerful illustration of these connections. It demonstrated that the violation of a fundamental geometric theorem, like Desargues' theorem, could be directly linked to a specific algebraic structure. This insight was crucial for understanding the diversity of projective planes and for developing a more comprehensive theory of projective geometry. It showed that the seemingly rigid framework of Euclidean geometry had a much richer and more complex landscape. The modern relevance of Moufang's work extends into contemporary mathematical research. Non-Desarguesian geometries, including the Moufang plane, continue to be objects of study. They provide valuable insights into the foundations of geometry. Furthermore, the connections between algebraic structures and geometric models, which Moufang pioneered, remain a central theme in modern mathematics. Her work has influenced areas like finite geometry, which deals with geometric structures with a finite number of points and lines. Finite geometries have applications in diverse fields, including coding theory and cryptography. The study of finite projective planes and their connection to algebraic structures is a vibrant area of research. The classification of finite projective planes remains an open problem, and Moufang's work provides a foundation for understanding the complexities involved. The legacy of Ruth Moufang's work on the Moufang plane is a testament to her profound mathematical insight. She was able to see beyond the established boundaries of mathematics. She forged a path that connected seemingly disparate fields, and her contributions continue to inspire mathematicians today. Her work highlights the power of abstract, algebraic methods to solve problems in geometry and to reveal the deep connections between different areas of mathematics. The Moufang plane and a broader methodology stand as a lasting contribution to the advancement of mathematical knowledge. The exploration of projective planes presents a fundamental challenge of their classification. Projective planes, while seemingly simple in their axiomatic structure, exhibit surprising diversity and complexity. Understanding the relationship between their geometric properties and underlying algebraic structures is at the heart of this classification problem. It was within this context that Ruth Moufang made her seminal contributions, culminating in what is now known as the Moufang theorem. The Moufang theorem provides a profound connection between the geometric properties of a projective plane and the algebraic properties of its coordinate ring. Specifically, it states that if a projective plane satisfies the Little-Desargues property with respect to three non-collinear points, then the plane is coordinatized by an alternative division ring. The Little-Desargues property, a weakened form of Desargues' theorem, holds when Desargues' theorem is only required to hold for triangles in a specific configuration. Desargues' theorem itself, a cornerstone of projective geometry, asserts that if two triangles are perspective from a point, meaning that the lines joining corresponding vertices concur at a single point, then they are perspective from a line, meaning that the corresponding sides intersect in points lying on a single line. The Little-Desargues property restricts this condition to triangles where the center of perspectivity lies on one of the sides of the triangles. Moufang's theorem demonstrates that this seemingly minor geometric condition has major algebraic implications. It links the geometric concept of perspectivity to the algebraic structure of alternative division rings. Alternative division rings, as discussed previously, are a generalization of division rings where the associative law of multiplication is relaxed to the alternative laws. These laws state that x times y is equal to x times xy, and y times x is equal to yx times x for all elements x and y in the ring. The significance of the Moufang theorem lies in its ability to characterize a specific class of projective planes, those coordinatized by alternative division rings. These planes, known as Moufang planes, occupy a special place in the hierarchy of projective planes. They represent a departure from the more familiar Desarguesian planes, which are coordinatized by division rings, while still retaining a high degree of algebraic structure. The theorem essentially provides a geometric test for determining whether a projective plane belongs to this important class. The proof of the Moufang theorem is a remarkable feat of mathematical ingenuity. It involves a delicate interplay between geometric arguments and algebraic manipulations. Moufang's original proof, published in 1933, is intricate and relies on a careful analysis of the collineations, or structure-preserving transformations, of the projective plane. She demonstrated that the existence of the Little-Desargues property implies the existence of certain types of collineations that, in turn, force the coordinate ring to satisfy the alternative laws. A key aspect of the proof involves constructing a coordinate system for the projective plane based on the three non-collinear points with respect to which the Little-Desargues property holds. Using this coordinate system, Moufang was able to express the geometric conditions imposed by the Little-Desargues property in terms of algebraic equations involving the coordinates of points and lines. By carefully manipulating these equations, she showed that the coordinate ring must satisfy the alternative laws. The proof is not straightforward. It requires a deep understanding of both projective geometry and abstract algebra. It involves a series of clever constructions and arguments that build upon each other to reach the desired conclusion. The intricate nature of the proof reflects the subtle relationship between geometry and algebra that the theorem reveals. The Moufang theorem has had a lasting impact on the study of projective geometry and related fields. It provides a powerful tool for classifying projective planes and for understanding the connection between their geometric and algebraic properties. The theorem has been generalized and extended in various directions, leading to a deeper understanding of the structure of non-Desarguesian planes. One important application of the Moufang theorem is the study of finite projective planes. As mentioned previously, the classification of finite projective planes is a major open problem in mathematics. The Moufang theorem provides a crucial piece of the puzzle by characterizing those finite projective planes that are coordinatized by alternative division rings. In the finite case, an alternative division ring is necessarily a finite field, and the corresponding projective plane is Desarguesian. Therefore, the Moufang theorem implies that any finite projective plane satisfying the Little-Desargues property must be Desarguesian. This result has important implications for the classification of finite projective planes as it restricts the possible structures that can occur. The Moufang theorem also has connections to other areas of mathematics such as Lie theory and algebraic groups. The Moufang planes are closely related to certain types of algebraic groups known as Moufang loops. These loops are non-associative generalizations of groups that arise in various contexts, including the study of symmetric spaces and the classification of simple algebraic groups. The connection between Moufang planes and Moufang loops provides a bridge between geometry, algebra, and group theory. The enduring influence of the Moufang theorem is a testament to its depth and significance. It remains a central result in the study of projective geometry and continues to inspire research in related fields. The theorem's ability to connect seemingly disparate areas of mathematics highlights the power of abstract algebraic methods to solve geometric problems and to reveal the deep connections between different branches of mathematics. The classification of projective planes, a challenging endeavor, is greatly aided by the Moufang theorem. Moufang's profound impact on mathematics extends far beyond the specific theorems and structures bearing her name. Her work reshaped the landscape of projective geometry and algebra, leaving an indelible mark on the way mathematicians approach these fields. She addressed fundamental questions about the nature of geometric space and the algebraic structures that underlie it, providing new tools and perspectives for understanding these concepts. The reception of Moufang's work during her lifetime was marked by both admiration and challenges. While her mathematical abilities were widely recognized, the prevailing academic environment presented obstacles for women pursuing careers in mathematics. Despite these difficulties, she persevered, establishing herself as a leading figure in her field and inspiring future generations of mathematicians. She navigated a world where opportunities were not always readily available, yet she carved out a space for herself through the sheer force of her intellect and dedication. One biographical detail that illuminates her commitment to mathematics is her early education and training. She received a solid foundation in mathematics and physics, which enabled her to pursue advanced studies and research. Her doctoral work, supervised by Max Dane, provided her with the opportunity to delve into the intricacies of projective geometry and to develop the ideas that would later form the basis of her most important contributions. This rigorous training, combined with her innate talent, set the stage for her groundbreaking work. Another significant aspect of her career was her long-term affiliation with the University of Frankfurt. There, she held various positions, eventually becoming a professor. This provided her with the platform to teach, mentor students, and conduct research, further solidifying her influence on the mathematical community. Her presence at Frankfurt contributed to the university's reputation as a center for mathematical excellence. The legacy of Ruth Moufang is one of the innovation, perseverance, and profound mathematical insight. She opened new avenues of research in projective geometry and algebra, demonstrating the power of abstract algebraic methods to solve geometric problems. Her work continues to inspire mathematicians today, shaping our understanding of fundamental mathematical structures. The Moufang planes, for instance, remain a vibrant area of research, with mathematicians exploring their connections to other areas of mathematics, such as Lie theory, algebraic groups, and finite geometry. The classification of these planes is an ongoing endeavor, with new results and insights emerging regularly. The study of Moufang loops, the algebraic structures associated with Moufang planes, is also an active area of research, with applications in various fields, including cryptography and coding theory. The Moufang theorem, a cornerstone of projective geometry, continues to be a subject of study and refinement. Mathematicians are exploring its generalizations and applications to other geometric settings. The theorem's ability to connect seemingly disparate areas of mathematics highlights the unifying power of abstract algebraic methods. It serves as a reminder that seemingly different branches of mathematics are often deeply interconnected, and that progress in one area can lead to breakthroughs in others. Her influence extends beyond the specific results and structures bearing her name. She inspired a generation of mathematicians to think differently about geometry and algebra, to embrace abstract methods, and to seek connections between different areas of mathematics. Her work challenged conventional wisdom and paved the way for new approaches to old problems. Moufang's legacy is further enhanced by her role as a mentor and teacher. She guided numerous students through their mathematical studies, instilling in them a love of mathematics and a commitment to rigorous scholarship. Her students went on to make their own contributions to mathematics, extending her influence and perpetuating her legacy. She fostered a collaborative and supportive environment, encouraging her students to explore their own ideas and to challenge existing paradigms. The enduring impact of Moufang's work is a testament to its depth and originality. She addressed fundamental questions about the nature of geometric space and the algebraic structures that underlie it, providing new tools and perspectives for understanding these concepts. Her contributions have had a lasting impact on both algebra and geometry, shaping the way mathematicians approach these fields. Her work stands as a reminder of the importance of perseverance, dedication, and intellectual curiosity in the pursuit of mathematical knowledge. She overcame significant obstacles to achieve her goals, demonstrating the power of the human spirit to overcome adversity. Her story is an inspiration to mathematicians of all backgrounds, reminding them that anything is possible with hard work and determination. In conclusion, Ruth Moufang's contributions to mathematics are profound and far-reaching. She revolutionized the study of projective geometry and algebra, leaving an indelible mark on these fields. Her innovative ideas, her rigorous methods, and her unwavering commitment to scholarship have inspired generations of mathematicians. Her legacy continues to shape our understanding of abstract mathematical structures, and her work will continue to be studied and admired for many years to come. The innovative nature of her work lies not only in the specific theorems she proved, but also in the way she approached mathematical problems. She combined geometric intuition with algebraic rigor, developing new methods for studying these structures. Her influence on subsequent mathematicians is undeniable, as her work has inspired countless researchers to explore the connections between geometry, algebra, and other areas of mathematics. Her lasting impact on both algebra and geometry is evident in the continued study and application of her ideas. The Moufang planes and Moufang loops remain active areas of research, with new results and insights emerging regularly. As researchers continue to explore the depths of these structures, they are building upon the foundations laid by Ruth Moufang, a true pioneer in the field of mathematics. The echoes of her work resonate throughout the mathematical landscape, a testament to her enduring legacy.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.